In the next module, we will just see a brief history of thermodynamics. Remember that we are not giving an account of all possible events that happened, because that is impossible. Unlike some other subjects like classical mechanics, where you know few people like Newton has introduced and developed the subject along with some other people, and statistical thermodynamics where Boltzmann had a huge contribution to it. Thermodynamics is a contribution of several people, several scientists, and for centuries, not just one century, for centuries people have tried to work, and then finally in 19th century the subject actually were properly formulated. And it will be interesting to know that in the laws of thermodynamics like first law, second law, third law, the second law, the most interesting, intriguing one, was the first one to come, and then the other laws actually came as a consequence of that. I will see that if you understand second law, we understand everything else. So, we will just talk about history of thermodynamics, and the history starts with Greek philosopher called Parmenides, who said that there cannot be any vacuum anywhere. So, nature abhors vacuum. So, he said that vacuum cannot exist. Probably right now it is easy for us to understand, knowing that what knowledge we have right now. However, if you go back to 5th century BC, to imagine that there cannot be any vacuum anywhere is a remarkable thing, and that theory or that idea that vacuum cannot exist was used by several scientists later on to do work or to make engines. For example, in 1638, around that time, Galileo showed that a vacuum pump can be used to raise water, and actually people knew about pump at that time, not like a normal electric pump that we know right now, like some vacuum can be created to pull up water. That kind of pump people knew about it, so he proposed that. And then Torricelli tried to create a vacuum. Again, lot of people tried to show that they can create vacuum. So, Torricelli's vacuum was that he filled in mercury in a small tube and then held it on the top, and then put it in mercury in this beaker, and then it created a small vacuum. It is not totally vacuum, right, on the top. It is called Torricelli's vacuum. So, it is actually a barometer, right, because it that what is happening here, the air pressure is pulling this level of mercury inside the tube. So, it is just a device for checking the pressure, air pressure. So, but he said that he created the vacuum on the top because there was nothing, no mercury present. And then there is a scientist called Guericke who used who demonstrated the power of vacuum by something called Magdeburg hemisphere. So, Magdeburg hemisphere consists of two hemispheres. So, he used his vacuum pump. So, he also built a vacuum pump. He used the vacuum pump to take out the air from inside of this hemisphere. So, he put the hemisphere together and then take out the air. So, that means now they will be joined together, and then he used 24 horses on both sides to pull that, and it was not possible even by 24 horses or 12 horses on each side, something like that. There stories are there for different number of horses, but he used lot of horses on both sides of this hemisphere and they could not pull it out. Okay. So, before I go further, we are going to demonstrate a little bit part of this vacuum, although we do not have Magdeburg hemisphere right now, and we do not have horses also. However, we can still show it. So, Raymond and I, we are going to, Raymond, you are going to do that yourself?
No.
So, this is one hemisphere, like half sphere. Hemisphere is like half sphere. This is another hemisphere, half sphere. Ideally, we should put it together and take the air out. Raymond, you do that, but we cannot do that. So, we are going to take the air out in a different way. Yeah, we are pushing the air out from this.
Now there is no air inside.
Now there is no air inside, and we are going to pull it You want to try it? So, only danger is that if you try it, you might break the other part, but come and try. Make sure don't leave it, huh? Then I will fall. Okay, good. So it requires, as you can see, that it requires a lot of force to take out when there is a vacuum. Of course, there was no full vacuum there, and the material was flexible enough that it could it could bend and twist, and that is the reason actually it came off. Had it been a normal metal one with a proper vacuum, he could not have pulled it for sure. So that is what he Guericke showed the power of vacuum around like 1654, 57 at that point of time, and it is so famous that there is a statue of Magdeburg hemisphere in Germany. So this is one of the beginning or onset of thermodynamic principles that is coming into the picture. See, people are doing the work. So when you use a vacuum pump, you are actually doing a work to create the vacuum, and then that vacuum can be used to do another work. So it is not that vacuum getting created by itself, you are creating the vacuum and then using the vacuum. So soon after, Boyle, we know Boyle's law, right? So Boyle used something like a vacuum pump air pump combination device called pneumatical engine, and that gives rise to Boyle's law. So you know about Boyle's law, right? What is Boyle's law? Pressure is inversely proportional to volume, right? So that thing is Boyle's law. So he showed that using this particular engine, and back in 1660. So then again similar, few years later, Christian Huygen used gunpowder to create vacuum. So you can use a gunpowder and remove the air out of that, and then so created the created an explosion with the gunpowder, and then use that vacuum to move a piston. So that piston could do work of like 4 or 5 people together. So using that particular vacuum. Then 1690, French scientist Papin, he used a prototype of steam engine which is called Papin's digester. Digester means bone digester, so which will actually like a pressure cooker which will digest the bone. So it is like a 2-step process. You heat it first, expand it, and then cool it, get it back to the first initial stage. So heating and cooling, these are the 2 steps that he used to create a prototype of an engine. Remember, any engine has to come to its initial position all the time, otherwise it is not going to work. Whenever you do an engine, it is always a cyclic process, that it has to come back to its first place. So he used this particular prototype, and you will see later on that it really helped in development of thermodynamics, because later on Carnot used a better version of that. Then Bernoulli is in almost like, as you can see, almost 50 years later on, Bernoulli used a billiard ball model to talk about statistical description of pressure, that the pressure is nothing but forces that is exerted by individual particles. So he proposed that around like 1730 at that time, but it was totally forgotten for a long time. Later on Maxwell actually revived that, and it gave rise to kinetic theory of gas, but Bernoulli was there for the first to actually show it, that he showed that temperature is actually square root of velocity. We will talk about that later on. Then 1765 again soon after. So we are now in 18th century. So James Watt used a steam engine, where his contribution was to make a separate condenser. So when you heat something, you have to cool it also. So how do you cool it? So initially everybody else before Watt, the cooling was in the same place as where the heating was, like you heat it and then you cool it. Like I have to put first on a heater and then I have to put on a cooler. That is not a very efficient system. So what James Watt did is that he used a separate condenser. So that increased the efficiency of the engine enormously. So that is one of the contributions, Watt's steam engine. And then at that similar at that particular time, around that time, Lavoisier claimed that heat is nothing but some kind of a fluid. It is called caloric fluid. That means, when you heat something, let us say heat water, that fluid goes into the water and heats the system. So, Lavoisier's caloric theory was disproven by Thomson, who used a canon boring experiment, where he used boring, that means try to make a hole with a cannonball, and it generated so much heat that the water in the container started boiling. So, he showed that this mechanical energy of boring can give rise to heat, which means that heat is no longer some other fluid. It has to do with something to do with this particular mechanical work that was done. So, he first indicated the relation between mechanical work and heat. Right now it is very obvious, but at that point of time it was a big discovery. Then came Carnot engine in 1824, where that Papin's engine he modified to make it a 7-step process. We will discuss about Carnot engine later on, because it is one of the most efficient engine possible. No, it is the most efficient engine. And later on, around 1843, Joule showed that heat is actually equivalent to kinetic energy. We are going to discuss precisely this particular experiment, Joule's paddle wheel experiment, later on. In fact, he said that when something falls, let us say a weight falls from some height to lower height, then what happens is that that potential energy gets converted to kinetic energy, right. So, this conversion of kinetic energy can be used to produce heat. So, that is why he wanted to measure the temperature at the top of the Niagara Falls and at the bottom of the Niagara Falls. Do you think the temperature will be different? Do you think the temperature will be different? Temperature is actually different, but that had to be measured on a cloudy day. So, in a normal day, the heat gets dissipated also, right. So, on a normal day when he measured, I think there was not much difference, but later on some other scientists did measure on a cloudy day and saw that there is a difference in the temperature on the top and on the bottom of the Niagara Falls. And the reason is very simple. Reason is that the kinetic energy that is getting produced by the fall of that particular water will produce the heat in the bottom part of the falls, and it actually is quite high. It is 52 meter fall, the fall of this thing. So, this particular Joule's experiment is related to the first law of thermodynamics. We are going to discuss that. And then Clausius around 1857 defined precisely a quantity called dq by T, heat by temperature, change of heat at a given temperature, and this he defined entropy as this particular quantity dq by T on his famous writing called On the Nature of Motion, that we call heat. The fact that motion is heat is a great discovery, believe it or not, which we take to be very granted now. At some point it was a remarkable thing. So, and then of course Maxwell gave rise to the kinetic theory of gases, where precisely one can see the relation between the motion and the temperature, motion of the particles and the temperature that we normally associate with a particular system. And little bit later, around 1872, Ludwig Boltzmann developed or gave a formulation of statistical thermodynamics, where all the observations that we have for a big system like glass of water can be understood from the motions of individual atoms itself, and that gave rise to a subject called statistical thermodynamics. We are going to also discuss a little bit of that. And there are many other scientists who contributed the development of thermodynamics, and we could not talk about all of them. As you see that it actually took centuries for this formulation to come into place, and the way we understand that. So, therefore, the importance of this particular theory is undeniable, and what Einstein said, that for all those different rules and laws that are there, thermodynamics is one of them which cannot seem to be overthrown so easily. It is a solid theory. So, this is a summary of the progress with time. Again, as I said, that there are a lot of other scientists' contribution which are not mentioned here. We try to give as many as possible with the important contribution of people here.